So now we're going to move into our agenda, and we're going to start out with our first talk from Dr. Don Boesch, who is Emeritus Professor and President and Emeritus President of the University of Maryland Center for Environmental Studies. He's one of the best known scientists in the world on issues of coastal eutrophication, and it's an incredible pleasure to have him here and have a chance for him to share his insights about nutrient management in the coastal zone. He's done a tremendous amount of work in this area, and he's going to connect that work today also to issues of climate change that we're facing. So I'm going to stop sharing here shortly, Don, so you can take over. So welcome, and thanks for coming to the Phosphorus Forum.
Well, thank you, Jim and Matt. I just, for the invitation, I just regret we're not having to have it in person as was originally scheduled last spring. And I'm eager to learn more about what you're doing. You know, the approaches to sustainable use of nutrients is really important for a whole variety of reasons. And so I'm looking to learn as well as to inform. And so I am going to talk about some coastal ecosystems and how the runoff and the discharge of nutrients, both nitrogen and phosphorus, can lead to coastal eutrophication with a lot of undesirable consequences, from harmful algal blooms to hypoxia and the like. And we are at the end of the pipe, as it were, and we're the in the coastal area are the recipients of what you send us down from the landscapes. And we have to try to manage in that broader context. Let's see, I'm trying, Matt, to advance my slide. And
you might try, are you, Don, can you use the arrows on your keyboard? Do those work all right? Or?
Yes, they do not work.
They don't work? Okay. You might click on the presentation once and then try it again. If that doesn't work, we can advance the slides for you.
Okay, maybe that, there you go. I clicked on the presentation.
Great.
So, you know, one of the things that separated our worlds in between what Jim does in limnology and in freshwater environments and in the coastal and ocean environments is that it's often thought that this issue of over-enrichment with nutrients is primarily a phosphorus problem in freshwater and primarily a nitrogen problem in coastal areas. And in truth, it's actually a lot more complex than that, as this kind of diagram from Hans Perl would indicate. There are multiple sources of both nutrients. There are lots of different things that go on within the aquatic systems that regenerate those nutrients or trap them, and as they go down to the coastal zone. And so this simplistic view is that, you know, these more limitation by phosphorus in freshwater and limitation by nitrogen in coastal zones. And as I said, it's not that complex. So there are many now, we've seen lakes where it's not simply a P problem, it's both, it could be co-limitation and both of the nutrients interact. And in the coastal zone, we similarly see many systems where there's an interaction between nitrogen and phosphorus in terms of limitation of biological productivity, and we need to think about managing both of those nutrients. In fact, some coastal systems are primarily phosphorus limited. So one of the reasons why this is the case, that there's a difference in the coastal area, is because of salt, because of the ocean. And the ocean, the salt in the ocean contains sulfate, as well as all the other sodium chloride and all the other minerals. And what happens is that as in sediments and coastal systems, that sulfates can be reduced to sulfide, and that has an effect of releasing phosphorus from sediments. So in many of these coastal sediments, there's a ready supply of phosphorus in the sediments that can be released, and the nitrogen burns out faster than the phosphorus. But as I said, it's not always that simple. And so here, this diagram shows you a recent analysis that's looked at this with some clever mathematical calculations in terms of water quality data based upon some older measurements of nutrient limitation, some experimental measurements involving small additions of nitrogen and phosphorus throughout the Chesapeake Bay. So here's the Chesapeake Bay watershed, and you can see it's a pretty large watershed. So what happens throughout that watershed comes down into the bay, and including half of the watershed, half of the water coming down comes down essentially from Pennsylvania and points north down the Susquehanna River. And so we have to manage those inputs throughout the basin. And that basin includes many different kinds of land uses, including extensive urban areas. These are the areas sort of in shades of purple and lavender, and including quite a considerable amount of agriculture. These are the areas in the reds and the maroons, and then of course extensive forested areas as well. So it's a complex landscape that has to be managed, and we've had to look upstream to get those results of reductions of those nutrient sources. So typically, what one sees is can you see my cursor here? No.
Yeah, yes. We can, Dan.
Okay, so here typically what one sees is that during the cooler months of the year in the spring, when that production is important, there's phosphorus limitation down quite a ways down through the bay from top in the Susquehanna River to the south. But then as there's more flushing and there's more salinity involved, it tends to be nitrogen limited. And that situation shifts. So what happens is that phosphorus is really important in stimulating that spring production, but then nitrogen is really important for maintaining that production, which continues to produce organic matter, which creates hypoxia in bottom waters and creates excess production, which is shading out seagrass beds and the like. So this has always long been seen as really a 2-nutrient challenge that has to be addressed. So I completed last year an assessment on a global basis of the major areas around the world where this large-scale coastal eutrophication is being tackled. And I won't be able to address all of those here, but suffice it to say that I'm going to show you some examples from not only the Chesapeake Bay, but also in Northwest Europe and the Baltic Sea and the North Sea, and then come back to the US and talk about the Gulf of Mexico and the Mississippi Basin. This synthesis that I did is looked at, how the problems were diagnosed, what are the management steps, what are the organizational programs to achieve results, and where are we with respect to the outcomes, and what do we need to do. So if you're interested more in that in a comparative way, I'd urge you to look at that publication. So in the Chesapeake, we started out in recognizing there were pretty extensive water quality problems, declining light penetration, increased algal biomass, and more hypoxia. We saw that back in the 70s, really. So in 1983, the states and the EPA got together and forged this first Chesapeake Bay Agreement. And it was basically, we're going to clean up the bay, and it didn't say much more than that. But by 1987, we pretty well had diagnosed that a root cause of a lot of the issues was over-enrichment with nutrients. And there was a goal set of a 40% reduction in both nitrogen and phosphorus loads. And we were very optimistic we could achieve that by the year 2000. Of course, 2000 came quicker than we thought, and we had really made very little progress in meeting those nutrient load reductions. But so there was another agreement. We're serious this time. We're really going to recommit. We're going to do all these things. We're going to base our reduction goals and allocation of those by science, and we're going to get the job done by 2010. Turns out, and it also said, we're serious this time. So if we fail in 2010, we're going to say we have to do this under the law, under the Clean Water Act. So 2010 came by. We missed it badly, and so there was an agreement a few years after that, which put the states agreed to go under a mandatory total maximum daily load program to reduce it, and with the goal that this would be achieved, these nutrient reduction goals would be achieved by 2025, which is just 5 years away from now. So we're now struggling to see exactly where we are and see if the gaps can be closed to meet that TMDL objective. So this is what the management community tells us where we are. It looks actually pretty good that we've been actually able to reduce those loads, both of nitrogen and phosphorus, and we're approaching the targets. But of course, we only have 5 years to go, so there's a long way to go, particularly for nitrogen, if you believe these graphs. The important thing to understand here is that of these various sources of inputs, only one of them, that is wastewater, is actually monitored and measured in any direct way. The others are estimated, usually using various models to help us understand what the activities that we're doing to reduce the nutrient loads, what their effects might be on downwater transportation and delivery to the bay. So we've relied on these models not only to set our management goals and to determine what are the steps we need to take, but also a little bit dangerously to sort of measure progress without consulting the real world. So as you can see, even based on this, say for nitrogen, we have seen a significant reduction of wastewater inputs through investments in advanced waste treatment with nitrogen removal. And we've seen the same thing for phosphorus, as you can see, tremendous reduction of phosphorus inputs from when we started in baseline of 85 to the present. And we're pretty certain that those are realistic because they're measured. For nitrogen, we've actually seen, in this graph shows it a little bit, but there's other data that suggest it's even more powerful, that there's been a significant reduction from atmospheric deposition sources of nitrogen because of actions we've taken to clean up air and reduce nitrogen oxides in the atmosphere. And it shows also some reduction from agricultural sources. But if you look then where we are now, you can quickly come to the understanding that we have to get the rest of the goal reductions largely from agriculture. And it's problematic in terms of the recent pace of load reductions from agriculture, say from 2009 to 2019, if we're able to do that, the present rates of progress. The other thing here, you'll see that while we're doing this, we're reducing sources, we're also spreading it across the landscape and urbanizing and developing land. And so based upon these management models, this is going the other direction, increasing the load of nitrogen and phosphorus from land development, from developed lands. A different challenge that we have to face. So here is, before I go into trying to check and see what we can determine from observations and check the models and what terms of what's really happening, let's talk about the fact that there's a lot of evidence to suggest that these reductions are real, not in terms of the quantity, but at least in terms of the direction. And we're seeing reductions of nutrient loads at the fall lines where the rivers enter the Chesapeake and those rivers that are monitored. We're also seeing some changes in improvements within the ecosystem. So here you see on this graph here, this shows you eventually the volume of hypoxia on an annual basis grouped by decades. And you can see it went from this situation and it got very worse, so that even given the nutrients loads went up, the amount of hypoxia went up. But now it seems since at least say the 1990s that we're having a smaller hypoxic area, even given as the nutrient loads reduce. So we're headed in the right direction. And here it kind of indicates a little bit why in terms of the feedbacks that are working. So in this case, you see this is the measurements over the long time of bottom water in the Chesapeake Bay. And what happens in these low oxygen waters, of course, is now we're seeing oxygen levels slowly improving. We also see ammonium levels. Ammonium's reduced nitrogen, and it's produced from decomposition of organic matter down from the sediments and in the bottom waters. And since there's little oxygen there, it doesn't nitrify, and so it remains as ammonium. And now we're seeing that going down in nitrate, which means that there's nitrification taking place going up. That's important because this is the process, the nitrification, denitrification coupling that removes the excess nitrogen from the aquatic system. So as we get closer to the goal, it's really important that we see not only redouble our efforts, but also as needed, but also really look hard at what these model predictions, model estimations are really showing. with respect to the real world. So this is a recent paper from Ator et al. And JEQ, which basically raises some serious questions. So here in the management model, you see this is although the year periods are different than what I showed in the other slides, the same trend, same data trend, same method of analysis. You can see this reduction of nitrogen from agriculture, but here you really see none. And in this case, you see actually an increase in nitrogen from developed land, and in this USGS analysis, which is based, if you're familiar with it, with the application of the SPARROW model, more of an empirical statistical analysis based on water quality, stream concentration, and load trends. You see that actually is not changing that much, not increasing that much. Here again, there's general agreement between wastewater. Obviously, that's measured. Also, for phosphorus, you see not only do these two approaches diverge, but they diverge in terms of even the direction. So the management model suggesting we've had significant reductions of phosphorus input, whereas these empirical SPARROW-based estimations over the same period actually showed that those inputs have increased, and including particularly because there's an increase in loadings from agriculture of phosphorus. Now, what is the reality? How do we explain these differences? So here it is. This is the comparison I talked about here, the management model versus the empirical model based on the water quality monitoring data. Management model suggests we should have about a 17% reduction of loads from agriculture delivered to the bay. Empirical model suggests it's near zero. And here it says there's an increase from developed land, and the empirical model has very little change. In fact, it's, and then for same thing for phosphorus, where there's this really not only a quantitative difference, but a directional difference in terms of management, the phosphorus loads from agriculture. So what's going on? First, of course, and we've known this a long time, and just sort of say, well, that's what it must be, is this issue of lag times. So there's I think you folks, many, including many in the agricultural and limnological community, know that there are lag times in these systems before we reduce the inputs. Lag times in the soil is because there's a buildup of material that takes a while to leach out. Lag times in the water, in the groundwater, and especially for nitrogen, of course, as this takes a while before this nitrogen leaches down the groundwater, and it may take decades before it actually you see a result into the streams in delivery to the bay. The models are different. There may be some assumptions in the model processes which could be explaining the differences. And then, of course, the other third option is that the assumptions that go into the management model about the level of BMP implementation, all based on what the state ag agencies report, things that were done over so many acres, whether they are actually implemented or implemented according to the best practices. And then also, it could well be that that the BMPs aren't as efficient as we assumed in the model world. And the other thing which is intriguing here is that these stream flow data, and there's other data that suggests this is true, that there's somehow more urban nutrient retention than we thought that's taking place, that we need to understand. So this has implications beyond the Chesapeake Bay, because this TMDL for the Chesapeake really has a national, even maybe international significance. It's the first time that the TMDL of that scale over multiple states and multiple watersheds has been implemented. And for that reason, it was challenged early on by the Farm Bureau Federation and a coalition of agribusiness under the Clean Water Act, and the courts, both the district court and the appeals court, ruled in favor of EPA and the states that it is consistent with the Clean Water Act. And here, this cartoon that's done at the time suggests that there's in the hinterland thinking, uh-oh, if you clean up the Chesapeake Bay, they're going to come after us next. Now, more recently, as we get closer to this 2025 objective, we'll see that we are falling short, and the states are in the lower bay, Maryland and Virginia, are pointing to EPA and pointing to their lack of strength and implementation with the state of Pennsylvania, which is well behind its goals, doesn't have a plan to get there and assuring meeting the TMDL. So stay tuned, there's going to be more legal action on that front. Going to Europe a little bit, and I'll have to hurry a little bit to get through this. Hopefully you'll have the presentation and the slides and you can look up these references. But some interesting results in Northern Europe. The North Sea, southern part of the North Sea on the European side rather than the British side has had serious water quality problems. And there's been a major effort to reduce the input of nutrients from the major rivers, the ones you know mostly about are the Rhine and the Elbe coming into this system. The flow takes that water to the north, so the impact of this has gone all the way up the coast onto the Wadden Sea area here and caused a lot of degradation of the water quality and habitats in that area. So the Europeans have been fairly have accomplished quite a bit in terms of load reductions. Initially, quite rapid load reductions for phosphorus. You know better than I where that's coming from. It's point sources for the most part, and there's still phosphorus input from non-point sources as we go here. And then a little bit later for nitrogen, again, largely dominated by treatment of point sources. So by 2010, we've had in this a system of 81% reduction of phosphorus inputs and 45% reduction of nitrogen inputs. The differences in how much we've been able to reduce those inputs and the time frame in which we've done it has produced some interesting results. So initially, phosphorus inputs, because it's so heavily nitrogen, there's such large loads of nitrogen compared to relative to the available phosphorus. The phosphorus reductions reduced primary production in this system, made it less phosphorus limited. And so that meant that we began to send more of that nitrogen to the north, causing more problems here. Now we've been able to reduce nitrogen levels to the point where these conditions along the coast here are improving. The Baltic is the world-class example where 9 nations around the Baltic are working to achieve these reduction inputs. And this is a quite complicated system, in a way somewhat like a lake, because internal load and retention of phosphorus, there's very little exchange from this system. So the phosphorus that's sent to the Baltic Sea tends to stay there in the sediments. It's released with low oxygen levels and continues to fuel excess production and particularly of noxious, harmful algal blooms, cyanobacterial blooms in the portion of the Baltic here. Whereas the coastal systems are often limited, it's a very low salinity area, often limited by nitrogen. So they have a special kind of 2-nitrogen problem to address. You can see where they are based upon their estimates. These are progress. These are based on observations more than models. And we still have a way to go with respect to phosphorus reductions. And even when that goal is met, it's estimated that it's going to take many decades for the water quality and the conditions of the Baltic to improve because of the large loads of phosphorus retained in the system. One particular interesting point is in Denmark, which is a small country, which has a large agricultural base, but surrounded by water. And so the public demanded a more active and aggressive role. And you can see here their history, where they've been able to reduce phosphorus inputs, again, from point sources pretty quickly, nitrogen point sources, and now are struggling to reduce diffuse sources of nitrogen. But this is actually now seen and witnessed not only in the groundwater concentrations, but in the stream concentrations delivered to the coastal waters of Denmark. This was done with a more of a regulatory regime, where there were really specific regulations with respect to fertilizer applications and surplus nutrient applications, cover crop requirements, things of this sort. And it's probably taken that to produce these kinds of results. Here, back to the U.S. and the infamous Gulf of Mexico dead zone. This is looking at the time here, this is the, what we're talking about. These is an area with a bottom water on the inner shelf. It goes largely, almost anoxic with very low oxygen conditions. And the source of the nutrient inputs is the Mississippi River. So in 2001, there was an action plan endorsed by the up basin states and EPA to reduce those inputs. There was no specific target, nutrient reduction target specified at the time. They just were going to take actions to reduce the scale and size of the dead zone of the hypoxia to about a third of what it had been. Now, this is a challenge because the extent of hypoxia goes up and down quite a bit, depending upon the river flow, but also depending on hurricanes. So for example, here, this year, we've got unexpectedly low extent of hypoxia because a hurricane passed just through the area just before the survey was done. So we need to find a better way that's more predictable about how the system is responding. It will respond, though, we think. These are some quite elegant applications of hydrodynamic models now based upon an accumulation of knowledge about how this system works. And here it shows that in the current loads, on the average, we would have an extent of this hypoxic zone like so. And if we were able to achieve what is now the interim reduction goal of a 20% load reduction, they would shrink and actually shrink more in volume than in footprint or area, which is good. But if we could reduce the loads, and this is just nitrogen, by the way, this model was just done for load reductions of nitrogen. If we could reduce nitrogen loads by 52%, we would get to the 1/3 area of it. We still have hypoxia develop almost every year, but it would be much smaller if we were able to do that. Now, there's been a lot of debate about the role of phosphorus in this, and at one point, someone who is, I think, was familiar with what I would call, Jim, the freshwater phosphorus hegemony, that it's only phosphorus, said, "Oh no, you're wrong. We need to reduce phosphorus." And everything slowed down, and that's because the N&P loads of the river are really high. I mean, you wouldn't expect nitrogen limitation near field. In fact, if you do bioassays, you'll see that the system is phosphorus limited near the river plume. But then, because of recycling and this recycling of phosphorus and so on, becomes nitrogen limit farther afield. So this is another interesting experiment by the same modeling group, which they basically said, well, let's just take a 60% load reduction. If we were to do that, here's the model projections over a year and how it would vary based upon the conditions that existed in 2009. We could get, if we just reduce phosphorus loads, we could reduce the extent to hypoxia like this. If we just reduce nitrogen loads, it'd be here. So you see nitrogen is more effective than phosphorus production. But if we could reduce both, we would get even more. So the new thinking is, how do you actually balance these two and work towards those objectives in the long run? Now, having said that, I don't have a lot of good news to show you, because actually, if we look at the trends, we'll see that, and these are flow-adjusted trends, and I've only shown you the central tendency. They're basically flat lines since we started this. No real changes in either total nitrogen and nitrate, or total phosphorus or orthophosphate. So either, again, we are fooling ourselves that we're not taking enough steps to reduce these loads. And indeed, in fact, this whole thing has gotten slow to start in the Mississippi Basin. And there's evidence. So for example, on a large scale, nitrogen use efficiency, the ratio of nitrogen that's removed in production to the nitrogen that's applied, really has gone down a little bit. And for phosphorus, it's remained fairly stable. There's a lot of controversy about lag times in this system. And say for nitrogen, whether there's a lot of lag time of nitrogen in the soil before it goes into the water courses. And this is, or whether this is because it's so heavily tile drained, there isn't a great lag time and it moves out pretty quickly. So all those things are challenges for the future. We know where the nitrogen and phosphorus is applied, where it's coming from, the delivered sources from these USGS SPARROW estimates. They're a little bit different for phosphorus. More pastures, more animals, and so on affect phosphorus than row crops and tile drainage for nitrogen. And so there's ability to target the efforts, but the states involved in this have really resisted any allocation load reductions by state, which is what occurred in the Chesapeake many years ago, and in Europe many years ago. And they've really resisted any kind of an allocation goal. So there's no real strategies, nutrient reduction strategies for the subbasins within the Mississippi Basin. And the title originally had something about climate change, and I decided it was just too much to include. Here's just one tempting thing that shows you that there's a lot of things that occur in the coastal zone that are going to affect how these systems respond. So here is an estimate for the Chesapeake Bay, and I'll just focus on this hypoxic area, less than 2 milligrams per liter, the model estimates. And it shows you that as climate changes, sea level rises, so that increases the volume of the bay and ventilates the bay, if you will. So that can reduce the hypoxic area. Inflows from increased freshwater inflows, increased nutrient inflows have the reverse effect. The big driver here, though, is temperature. And that's just because as these systems warm up, the metabolism warms up, the stratification increases, and you have more hypoxia. So I think I don't want to go over time. And so here are the key points, and I'll just leave you to read them while I emphasize just a few. Coastal systems require careful attention to both nitrogen and phosphorus loads. In some cases, one's more important than the other. We really need to do a better job of reconciling what we think is going on with respect to our management models to real observations in the real world that factor in intelligent ways to model lag times. We need to understand that wastewater point sources have been most reduced, rapid results, but our challenges are diffuse sources by and large, and that reducing those sources will probably take something that would involve more like regulation or performance compliance rather than, as I said in the paper, the pay the polluter approach. We really need to get something out of it and making sure that the results are really obtained. So thanks very much.
Thank you, Don. So let us take a time for a couple of questions, please. So raise your hand if you'd like to ask one. I appreciated all those comments, Don. You know, this is the Sustainable Phosphorus Alliance, but I've also spent a lot of time advocating for a balanced approach to nitrogen and phosphorus in biogeochemistry and in eutrophication. So fascinating to see those results. It's interesting, you know, those trends in differential removal of phosphorus and nitrogen seem to be more and more widespread. I was just involved in a paper from China where it demonstrated that differential phosphorus removal during wastewater treatment is driving lake nitrogen phosphorus ratios up.
Right.
So it's kind of an interesting outcome. I see a question from Ed Weinberg.
Actually, we got Emmy Liu first.
Sorry.
Hi, Don. My name is Emmy Liu. I work in Iowa DNR. So we are in the middle of a voluntary nutrient reduction strategy. It has been going on for a number of years. I'm working on the point source, but also pay attention to the
It looks like we lost your audio, Emmy. Okay, well, we'll move on.
Let me just say, okay. You know, the states in the basin are at various levels of them developing nutrient reduction control strategies. And they're later to develop. Some of them are making progress. And some states, like Iowa, have other problems rather than the Mississippi. They've got groundwater contamination and drinking water contamination issues to worry about for nitrogen. And that recent papers have suggested that those efforts to manage the sources haven't yet yielded real measurable results. And the stream concentrations of nitrogen are actually still going up. And there are multiple factors of this. One of them is this growth and expansion of tile drainage, and largely driven by, you know, the demand for more corn production, for ethanol production and things of that, which make the systems more leaky of the fertilizers and so on we put on them. So it is a complex problem that we have to manage drainage, we have to manage application, we have to manage the things that retain the nutrients, wetlands, swamps, and so on in the basin.
Yeah, let's let Ed have his question, and then we'll move on to Carrie.
Great, thank you. Can you hear me?
Yes.
Yes, we can.
All right, so that's 100% improvement over yesterday, but I am concerned. Hopefully, I'll be able to ask my question before losing the microphone. So Don, very nice presentation. I have a question at the very beginning with that Pearl image of the watershed.
Mm-hmm.
So I noticed there was a nutrient call out right at the dam at that lake. But what caught my eye was it was nitrogen and silica. So at first glance, I thought it might have been sediments, but there was no phosphorus. So what's going on there, and why silica?
I can't remember which figure you're referring to, but it does remind me I needed to mention one thing when I talked about the Chesapeake. When it doesn't answer your question fully with respect to silica, but because silica is another issue that needs to be considered. But one of the things that seems to be occurring in the Chesapeake is the main dams in the lower Susquehanna are now essentially filled with sediments. So even though we're maybe reducing phosphorus.
Audio cut out.
Okay, that's a bummer. Anyway, sorry, Don.
It just unmuted. Am I unmuted?
Yes, now you are.
I'm just telling you that the trapping in dams complicates the factor, and you can cause a setback because you get to the point where you get more erosion, more input. Not only no trapping in the dams, but you get periodic erosion of the material, particularly for phosphorus, and it sends it downstream.